There's something hauntingly beautiful about broken things, objects pushed to their limits, left drifting in the void, only to stumble upon revelations that rewrite history. Picture this, a satellite mangled by the relentless chaos of space, its systems failing, its mission seemingly over, but in its final moments, as cosmic static crackles through its damaged circuits, it does the impossible. It captures a signal, not just any signal, but a whisper from the very edge of time itself. This isn't a scene from a sci-fi epic. This really happened. And what that dying satellite found, it's the closest we've ever come to witnessing the universe's first breath. Think about the odds. Out of all the instruments humanity has ever launched into the cosmos, it wasn't the pristine, billion-dollar observatories that made this discovery. It was a machine on its last legs, a forgotten relic spinning through the darkness, yet somehow, through a twist of fate, or perhaps the universe's strange sense of humor, it glimpsed the moment time began. The implications are staggering. If we can peer back that far, what else might we uncover about the fabric of reality? How much of what we think we know about space, about existence, is waiting to be appended? This is the story of how a broken satellite became our time machine. It's a tale of cosmic serendipity, of flawed technology revealing flawless truths. And it all starts with a signal, one that shouldn't exist, one that defies every expectation. What you're about to hear will stretch your imagination, challenge your understanding of physics, and maybe even make you question the very nature of time. Because when a machine meant to study distant stars accidentally records the echo of creation itself, you know you're in for a journey unlike any other. So let's rewind the clock all the way back to the beginning. The satellite was built for precision, a masterpiece of human engineering designed to listen to the faintest whispers of the cosmos. Its mission, to study cosmic microwave background radiation, the ancient light left over from the Big Bang, a relic from when the universe was just a newborn, barely 380,000 years old. Imagine tuning a radio to static, but hidden in that hiss are the fingerprints of creation itself. That's what this satellite was meant to capture, a baby picture of the universe. Launched by a team of international space agencies, it carried instruments so sensitive they could detect temperature variations as tiny as 1/1,000,000th of a degree. Scientists hoped these measurements would reveal secrets about how galaxies formed, how matter clumped together in the early universe, even clues about dark energy. For years, it worked flawlessly, dutifully mapping the cosmic microwave background with painstaking accuracy. But space is merciless, a place where radiation, micrometeoroids, and extreme temperatures wear even the sturdiest machines down. And then the unthinkable happened. Systems began failing, sensors glitched. The satellite, once a pinnacle of human achievement, started drifting toward oblivion. Yet in its death throes, something extraordinary occurred. As its damaged instruments scrambled to function, they picked up a signal unlike anything in the mission's original parameters. It wasn't just noise, it wasn't an error. Buried in the chaos of failing hardware was a pattern, a whisper from even further back in time than the cosmic microwave background. This wasn't the afterglow of the Big Bang. This was something older, something primordial. The satellite, in its broken state, had inadvertently tuned into a frequency no one thought possible to detect. It was like a detective stumbling upon a crime scene, only to realize they just uncovered evidence of an entirely different mystery. What made this discovery so staggering wasn't just the signal itself, but the sheer improbability of it. Scientists had spent decades building pristine observatories, calibrating them to perfection, all in pursuit of the universe's oldest secrets. Yet here was a battered, half-dead machine, a cosmic underdog revealing something even more profound. Sometimes it's not the flawless tool that changes history. Sometimes it's the one that's cracked just enough to let the light slip through in ways no one anticipated. And that light, it would rewrite our understanding of time itself. The engineers monitoring the satellite's data stream didn't panic at first. Space missions are full of glitches, cosmic interference, solar flares, even the occasional software hiccup. But this was different. The primary sensor, designed to map the faint afterglow of the Big Bang, started spitting out numbers that made no sense. Instead of the smooth, predictable fluctuations of cosmic microwave radiation, the readings pulsed with an eerie regularity, like a heartbeat echoing across 13.8 billion years. At Mission Control, someone joked about aliens. Then the laughter died because the pulses weren't noise, they weren't malfunctions. When the team isolated the signal, stripping away every possible instrumental error, what remained defied explanation. The rhythm was too precise, too deliberate. It lined up with no known astrophysical phenomenon, no quasar, no pulsar, no natural process in the universe's playbook. Worse yet, the signal seemed to emerge from a time before the cosmic microwave background itself. That was impossible. The cosmic microwave background is the oldest light we can see, the edge of our observational horizon. Nothing should exist beyond it, yet here it was, a whisper from the shadows of time, a message etched into the universe before atoms even formed. The implications sent shockwaves through the scientific community. If this signal was real, it meant our understanding of the Big Bang was incomplete. Maybe the universe didn't begin in a single explosive moment. Maybe there was a before, a phase so alien, so incomprehensible, that its traces lingered like ghosts in the data of a dying satellite. What made the discovery even more unsettling was how it was found. The satellite's failing hardware, its sensors half blinded by cosmic wear and tear, had accidentally tuned into a frequency no one thought to look for. Perfection wouldn't have caught this. Only brokenness, a glitch in the machine mirroring some deeper glitch in reality, could have revealed it. The team scrambled to verify the data, running simulations, checking for contamination, even consulting rival research groups. But the signal held. It was real, and so, a mission meant to study the afterglow of creation stumbled upon something far stranger. Evidence that time itself might have a memory, that the universe keeps secrets even older than light. The satellite, in its final moments, had become a cosmic archaeologist, digging deeper into the past than anyone dreamed possible. What it unearthed wasn't just a new piece of the puzzle. It was the unsettling realization that the puzzle might be infinitely bigger than we imagined. Decoding this anomaly wasn't just a scientific challenge, it was a race against time. The satellite's power was failing, its transmissions growing fainter by the hour, while on Earth, teams of astrophysicists and data analysts worked in shifts, poring over the erratic signals. At first, they assumed instrument failure. Maybe radiation had scrambled the sensors. Perhaps cosmic rays had artificially created this pulse in the data. But when they cross-referenced the readings with other telescopes and ran exhaustive simulations, the truth became undeniable. These weren't errors, they were echoes. The pulses aligned perfectly with theoretical models of quantum fluctuations, those infinitesimal ripples in space-time, predicted to have occurred in the first fractions of a second after the Big Bang. Think of it like this: if the cosmic microwave background is a photograph of the universe as a toddler, this signal was an ultrasound from its embryonic phase. Except no one thought we'd ever detect such a thing. The energy signatures from that early should have been erased by inflation, stretched into oblivion by the universe's explosive expansion. Yet here they were, preserved in the static of a malfunctioning machine. Here's where things get even stranger. The satellite's very breakdown may have been the key to its discovery. One of its damaged sensors, originally designed to filter out interference, had begun picking up faint, low-frequency waves it normally would have ignored. It was like a photographer accidentally removing their lens cap only to capture a once-in-a-lifetime shot. The flaw in the hardware had essentially turned the satellite into an unintended quantum archaeologist, digging deeper into cosmic history than any pristine instrument could. Scientists quickly realized this wasn't just about detecting ancient signals, it was about challenging fundamental assumptions. Mainstream cosmology holds that information from the universe's first moments is permanently lost, scrambled by inflation. But if a half-dead satellite could recover traces of that epoch, what else might we be missing? Could other, broken detectors, neutrino observatories, gravitational wave antennas be tuned to listen for similar whispers? The discovery sparked a radical idea. Maybe perfection isn't what we need to peer into the deepest mysteries of the cosmos. Maybe we need instruments that fail in just the right way. This revelation forced researchers to confront an uncomfortable truth. For decades, they'd been building increasingly precise tools to study the universe, eliminating every possible source of noise. But what if some answers aren't hidden in the signal? What if they're buried in the noise itself? The satellite's greatest gift wasn't just the data it collected, it was the paradigm shift it triggered. Sometimes the cracks in our understanding aren't obstacles, they're windows, and through this particular window, we're glimpsing a universe far stranger, far more dynamic than we ever imagined. The satellite's damaged sensor wasn't just failing, it was transforming into something far more valuable than its original design. Imagine a telescope with a cracked lens. Normally, that flaw would render it useless, but what if that very crack bent light in an unexpected way, revealing stars no one knew existed? That's precisely what happened here. As the sensor's shielding degraded, cosmic radiation seeped in, warping its ability to filter signals the way engineers intended. Instead of discarding anomalous readings as noise, this accidental defect turned the instrument into an entirely new kind of detector, one sensitive to frequencies physics had long considered impossible to observe. These weren't just random blips in the data. The signals pulsed with mathematical precision, forming patterns that aligned eerily well with speculative theories about quantum gravity. Some researchers had predicted such traces might exist, tiny ripples in spacetime from the universe's first trillionth of a second, when all known laws of physics temporarily broke down. But no one expected we'd ever detect them. The energy required to preserve these echoes across 13.8 billion years should have erased them completely. Yet here they were, imprinted in the static of a malfunctioning machine like cosmic fingerprints on a broken window. What makes this discovery so revolutionary isn't just the data itself, but what it implies about our tools. For centuries, science has operated on a simple principle: build perfect instruments to eliminate errors, but space keeps teaching us that perfection might be overrated. The Hubble Space Telescope launched with a flawed mirror, yet that very flaw led to unexpected discoveries about distant galaxies. The Kepler planet hunting mission continued finding exoplanets even after mechanical failures forced engineers to improvise new observation methods. Now, this dying satellite joins their ranks, proving that sometimes the universe reveals its secrets not despite our failures, but because of them. The implications ripple far beyond astronomy. Modern physics has hit theoretical walls: dark energy, quantum gravity. The nature of time itself resists explanation under current models. What if part of the problem isn't our theories, but our tools? We've been building detectors to confirm what we already suspect. filtering out anything that doesn't fit established paradigms. But reality, as this battered satellite proved, might be whispering its truths in frequencies we've been systematically ignoring. The real breakthrough here isn't just a new piece of cosmic history, it's a radical suggestion that the answers we seek might be hiding in the static, the glitches, the beautiful imperfections we've spent decades trying to eliminate. As engineers analyzed the satellite's final transmissions, they noticed something haunting. The cleaner they tried to make the signal, the more the anomaly faded. Only by embracing the sensor's flaws, its erratic behavior, its corrupted data, did the pattern remain clear. It's as if the universe was leaving breadcrumbs in the cracks of reality, visible only to those willing to look at their instruments not as broken tools, but as accidental gateways. This changes everything, because if a damaged satellite can glimpse time zero, what other doors might we unlock by designing detectors that fail in just the right ways? The cosmos has always been stranger than we imagined. Now we know it might also be louder if we learn to listen through the noise. The data streaming from that dying satellite didn't just rewrite textbooks, it shattered our most fundamental assumptions about time. Those oscillations in space-time weren't mere echoes of the Big Bang. They were something far more profound, a live recording of time itself flickering into existence. Picture the universe in its first unimaginable fraction of a second, a seething quantum foam where the very fabric of reality churned like a stormy ocean. In that chaos, time wasn't the steady river we experience today. It was more like lightning crackling unpredictably, stuttering into being, then vanishing again as space-time struggled to stabilize. What the satellite captured were the birth pangs of time as a dimension. The signals showed distinct patterns, ripples of energy pulsing at frequencies so high, they'd make an atomic clock seem sluggish. These weren't random fluctuations, they matched theoretical predictions of quantum gravity effects, where space-time isn't smooth but granular, like the pixels on a screen. Each pulse represented a moment when time itself clicked into place, as if the universe was still figuring out how to be a universe. This changes everything we thought we knew about the early cosmos. For decades, physicists assumed time emerged smoothly from the Big Bang, an unbroken thread stretching forward, but the satellite's data suggests something far wilder. Time didn't just begin, it stuttered, rebooted, and reconfigured itself repeatedly in those first moments. Imagine building a clock where the gears keep jamming, then lurching forward unpredictably. That's what the dawn of time looked like. The most mind-bending part, these oscillations weren't just a historical curiosity, they left permanent scars on the universe. The satellite detected faint imprints in the cosmic microwave background, subtle distortions that shouldn't exist if time had always flowed evenly. It's as if the universe's toddler phase left fingerprints on everything that came after, hidden in plain sight for 13.8 billion years. What does this mean for us? If time wasn't born perfect, if it had to evolve like everything else, then our perception of it might be incomplete. Could there be places in the cosmos where time still behaves differently, where those early instabilities never fully smoothed out? The satellite's final gift was proof that reality's most basic building blocks are stranger, more dynamic than we ever dreamed. And the most astonishing part, we only heard this cosmic whisper because a machine broke in exactly the right way. Einstein's vision of time as a smooth, unbreakable river, a fundamental tenet of relativity, has shaped our understanding of the cosmos for over a century. But the satellite's dying transmission didn't just challenge that idea, it tore it apart. Those erratic pulses weren't glitches, they were cosmic breadcrumbs leading us to a truth far stranger. Time didn't flow seamlessly into existence. It hiccuped, it stuttered. Like a film reel with missing frames, the early universe might have flickered in and out of being, with moments where time itself blinked off before restarting. This isn't just a tweak to the rules, it's a revolution. If time is granular, built from discrete quantum chunks instead of a continuous stream, then everything we thought we knew about causality, entropy, even the speed of light, might need rethinking. Imagine watching a video where the pixels themselves decide when to update. That's the universe these findings suggest, a place where time isn't the steady conductor of events, but a jittery participant, its rhythm dictated by quantum rules we're only beginning to grasp. The debate among physicists is electric. Traditionalists argue the satellite's data must be an artifact, a quirk of its failing hardware, but a growing faction sees something deeper. They point to theoretical work on loop quantum gravity, where spacetime isn't smooth but woven from tiny, indivisible threads. In this view, the satellite didn't malfunction, it glimpsed the stitches in reality's fabric. The pulses match predictions of how these quantum threads might vibrate in the universe's first moments, like echoes from a cosmic loom. What's at stake isn't just academic. If time is granular, it could explain some of physics' biggest mysteries. Dark energy, maybe it's not a mysterious force, but a side effect of time's quantum structure. The singularity inside black holes, perhaps it's not infinitely dense, just a place where time's pixels stop updating altogether. Even our perception of a now might be an illusion, a trick of scale, like mistaking a movie's motion for reality when it's really just 24 frames a second. The satellite's greatest irony, it was built to confirm Einstein's universe. Instead, its broken sensors opened a door to a wilder one. And if time itself is up for grabs, what other certainties might crumble? The answers won't come easy, but one thing's clear: the universe loves a good plot twist, and this might be its best yet. Those erratic pulses from the dying satellite didn't just rewrite cosmic history, they handed physicists a Rosetta Stone for decoding reality's deepest mystery. For over a century, Einstein's general relativity and quantum mechanics have been locked in an unresolved battle, each describing fundamental aspects of the universe but in languages so different, they might as well be from separate dimensions. Relativity paints time as a smooth, unbreakable fabric. Quantum mechanics treats it as a mere backdrop for particle interactions. The satellite's data suggests they're both right and both spectacularly incomplete. Buried in those glitching transmissions was a rhythm that quantum gravity theorists had dreamed of but never expected to see. Discrete ticks, like a cosmic metronome, marking moments when time itself emerged from the quantum fog. Imagine shaking a snow globe and watching the flakes suddenly align into perfect grid lines. That's essentially what the satellite recorded. The pulses match theoretical predictions of how spacetime might condense from a froth of quantum fluctuations, transitioning from a realm where past, present, and future blur together into the orderly flow we experience. It's as if we've caught the universe in the act of inventing time. This revelation cracks open a door physicists have been pounding on for decades. Quantum gravity models like loop quantum theory and string theory have long suggested that time isn't fundamental but emergent, a side effect of deeper quantum processes. Think of it like temperature. We experience it as real, but it's really just the average motion of countless molecules. Similarly, time might be what happens when countless quantum interactions reach a critical scale, like droplets forming in a cloud. The satellite's dying gasps provided the first experimental whisper that this wild idea could be true. The implications ripple across every corner of physics. If time emerges from quantum interactions, then the arrow of time, why we remember the past but not the future, might stem from quantum decoherence. In simple terms, as quantum possibilities collapse into definite states, they could create an irreversible cascade that our brains perceive as time's flow. Even black holes, those notorious breakers of physics rules, start making more sense. Their singularities might not be infinities, but places where the quantum substrate of time becomes too frayed to sustain our familiar reality. But here's the twist that makes theorists both thrilled and uneasy. The satellite's data suggests this quantum to classical transition wasn't clean. Those pulses weren't uniform. Some came in clusters, others spaced erratically, as if time sputtered like an engine on a cold morning before finally turning over. This challenges even the boldest quantum gravity models, hinting at processes more chaotic than anyone predicted. It's like discovering that a symphony's beautiful melody actually began as musicians randomly tuning their instruments until, by some miracle, harmony emerged. The most tantalizing clue: the pulse's frequencies align with calculations from an obscure branch of physics called causal set theory, which proposes that spacetime is built from discrete atoms of causality. In this view, the early universe wasn't just a hot soup of particles, it was a seething network of potential cause and effect relationships, flickering in and out of existence until enough connections stabilized to create continuous time. The satellite might have captured the moment when quantum randomness first knitted itself into the fabric of cause and effect we take for granted. What's astonishing isn't just that these theories might be right, it's that we're seeing evidence at all. Quantum gravity operates at the Planck scale, a realm so tiny, observing it directly would require a particle accelerator the size of the Milky Way. Yet here, in the death throes of a broken machine, nature handed us a backdoor. The satellite's damaged sensors, by pure cosmic luck, became sensitive to macroscopic traces of processes that should have been invisible. Sometimes truth doesn't just hide in the details, it hides in the cracks between them. This changes the game for how we search for quantum gravity's fingerprints. Forget building ever more perfect detectors. The real breakthroughs might come from instruments designed to embrace controlled imperfection sensors that fail in strategic ways, tuned to catch what flawless equipment would filter out. After all, if a dying satellite could glimpse time's quantum origins, imagine what we might discover by listening to the universe not just with precision, but with poetic asymmetry. The cosmos has always whispered its secrets in broken symmetries and beautiful flaws. We're finally learning to hear the static as a song. Cosmic echoes don't fade like sound in an empty room. They linger, stretched thin across the universe but never entirely gone. The satellite's final act was to catch these whispers, not with the precision of a finely tuned instrument, but through the chaotic static of its own decay. Like a microphone dropped into a canyon, its broken sensors amplified what should have been inaudible, ripples in space-time from the universe's first violent shudders. These weren't just remnants of the Big Bang, they were tremors from the moment reality first learned to vibrate, imprinted on the cosmos like grooves in a record. What makes these echoes so extraordinary isn't just their age, it's their fragility. Theory suggested they should have dissolved eons ago, smoothed into nothingness by the expansion of the universe. Yet here they were, faint but unmistakable, like finding a fingerprint on a fossil. The satellite's malfunction acted like a cosmic magnifying glass, its failing electronics accidentally tuned to frequencies no one thought to search. Imagine trying to hear a conversation across a crowded stadium by cupping your hands around a shattered glass somehow. The very breakage focused the signal. This discovery flips the script on how we study the early universe. For decades, cosmologists chased the cosmic microwave background, treating it as the ultimate boundary of observation. But these primordial time waves come from even further back, from an era before light itself could travel freely. They're not electromagnetic signals but vibrations in the fabric of spacetime, a direct recording of the universe's quantum infancy. Detecting them is like hearing the first cry of a newborn cosmos, a sound not carried through air but etched into the walls of reality. The implications are dizzying. If these echoes can be mapped, they might reveal hidden structures in space-time itself, wrinkles and folds from when the universe was smaller than an atom. Some theorists speculate they could even contain traces of earlier cosmic cycles, hints of a multiverse or evidence of a bounce from a previous collapse. It's archaeology on a cosmic scale, where the artifacts aren't pottery shards but quantum fluctuations frozen in time. Yet the real lesson here isn't just about the universe, it's about how we explore it. Science often assumes progress comes from ever greater precision, from polishing lenses and sharpening algorithms until every error is scrubbed away. But this satellite, in its glorious brokenness, reminds us that sometimes the universe speaks loudest through the cracks. The next frontier of cosmology might not lie in building better telescopes, but in designing tools that fail in illuminating ways, machines that listen not just for the universe's voice, but for its stutters, its glitches, the places where reality itself seems to hesitate. Because if a dying satellite can hear the birth of time, who knows what other echoes might be waiting in the static? For over half a century, cosmology textbooks painted the birth of the universe with broad, elegant strokes, a singularity swelling into smooth expansion like a perfectly rising cake. But the satellite's cracked lens revealed a far messier kitchen. Those erratic pulses weren't just noise, they were brushstrokes from a cosmic Jackson Pollock, showing a primordial universe that didn't inflate so much as splatter. The data suggests space-time didn't stretch uniformly in those first moments, but bubbled and fractured, expanding in fits and starts like ice cracking on a frozen lake. This changes how we understand one of cosmology's biggest puzzles: why matter clumped together at all. In the old smooth inflation model, the universe should have ended up homogeneous, a bland cosmic soup with no galaxies, no stars, just particles spread evenly like sprinkles in a perfectly mixed batter. Yet we live in a universe of texture where galaxies gather in filaments and voids like foam on the surface of a latte. The satellite's data finally explains why. Those early space-time tremors, the ones captured by its failing sensors, acted like cosmic seeds. Where space-time stretched thinner, matter pooled. Where it compacted, voids formed. The universe's large-scale structure isn't random. It's a fossil of space-time's turbulent infancy. Even more radical is what this implies about inflation itself. A prevailing theory held that space-time expanded faster than light in the first fraction of a second, driven by a mysterious inflationary field. But the satellite's readings suggest this expansion wasn't a single, smooth event. It was more like popcorn popping, uneven bursts of growth with quantum fluctuations magnified into cosmic proportions. Some regions of space-time ballooned while others lagged, creating density variations that became the scaffolding for everything we see today. Textbook diagrams of the Big Bang, those tidy concentric circles showing a neat explosion, now seem hopelessly naive. Reality was more like a boiling pot, with space-time frothing at scales we're only beginning to comprehend. This isn't just academic nuance. It reshapes how we search for dark matter, model galaxy formation, even interpret gravitational wave signals. If the early universe was this chaotic, then anomalies we've been dismissing as noise might actually be echoes of its fractal birth. The most poetic twist, this revelation came from a machine built to confirm old theories. Like a medieval mapmaker stumbling off the edge of their parchment, the satellite's broken sensors charted territories beyond our imagination. Its final transmission wasn't just data. It was a cosmic correction slip scribbled in quantum static and delivered just before the lights went out. Now the real work begins, rewriting not just textbooks, but our very conception of creation's first breath. Time's arrow has always been one of physics' most stubborn mysteries. Why does an egg splatter but never reassemble? Why do we remember the past but not the future? The satellite's glitching sensors may have finally pointed to an answer, buried in those erratic pulses from the dawn of reality. What they revealed wasn't just chaos, but a subtle skew in the universe's earliest moments, a tiny, quantum-level lopsidedness that set time's irreversible march in motion. Picture a deck of cards shuffled for the very first time. In a perfectly symmetrical universe, every shuffle would balance out, leaving no net change. But the satellite's data shows the cosmic deck was stacked from the beginning. Those pulses weren't random, they leaned ever so slightly toward one pattern over another, like a coin that lands heads up just 51% of the time. Over countless quantum interactions, that 1% bias snowballed into the overwhelming forward drive we experience as time's arrow. It's as if the universe, in its first flickering moments, tripped over its own feet and has been tumbling forward ever since. This asymmetry isn't just theoretical. The satellite detected it etched into space-time itself, a faint but consistent directional warp in the quantum foam. Imagine dragging a needle through wet clay. The grooves it leaves behind don't vanish when you lift the needle. Similarly, those early quantum fluctuations left permanent tracks in the fabric of reality, creating what physicists call preferred paths for cause and effect. Once enough particles started rolling downhill along these paths, there was no going back. The universe had tipped from maybe to must. The implications rewrite one of thermodynamics' oldest puzzles, entropy. We've long known systems trend toward disorder. Ice melts, perfume disperses, stars burn out, but never why the universe started so ordered to begin with. The satellite's data suggests the answer lies in those first asymmetric tremors. The slight imbalance didn't just dictate time's direction, it set the initial conditions for entropy itself, like a casino rigging its roulette wheel to ensure the house always wins in the long run. Here's where it gets wild. If time's arrow stems from quantum asymmetry, then our perception of cause and effect might be a cosmic accident. In a mirror universe where the imbalance leaned the opposite way, eggs might unscramble themselves and people would remember tomorrow while dreading yesterday. Even black holes, those notorious entropy factories, might behave differently under reversed conditions, perhaps emitting organized energy instead of chaotic radiation. But the real mind bender, this asymmetry might not be unique to our universe. If multiverse theories hold, other cosmic bubbles could have arrows pointing every which way, some where time flows backward, others where it loops like a Möbius strip. Our unidirectional experience of reality would just be a quirk of local physics, like living on a slope and assuming all rivers must flow downhill. The satellite's greatest gift wasn't just solving an old mystery, it was revealing how fragile our experience of time really is. Tilt the quantum scales by a fraction less in those first moments, and reality as we know it might never have cohered. The fact that we're here to ponder it at all could be the ultimate testament to a universe that, for all its chaos, got just lopsided enough to matter. Here's where the mystery deepens. Those erratic pulses from the dying satellite didn't just map onto empty space. They clustered in regions where dark matter, that invisible cosmic scaffolding, is known to lurk in abundance. At first, scientists dismissed it as coincidence, but the correlation was too precise to ignore. Every time the satellite's failing sensors picked up one of those primordial time ripples, it seemed to echo from the heart of a dark matter halo, as if the universe's hidden mass was whispering back. This wasn't just a curious alignment, it was a clue that dark matter might be more than a passive ingredient in the cosmic recipe. Some theorists now suspect it played an active role in stitching time itself into existence. Think of it like this: if space-time is a vast tapestry, dark matter could be the invisible threads holding its earliest stitches together. The pulses suggest that where dark matter pooled, time didn't just flow, it crystallized, stabilizing the quantum chaos into something measurable. Without it, the universe might have remained a formless, timeless froth. The implications are staggering. Dark matter has long been treated as a gravitational placeholder, an unseen hand that molds galaxies but doesn't interact with light or matter in any other way. But if it's directly entangled with time's structure, then everything we thought we knew about its nature might be upside down. Perhaps dark matter isn't just some exotic particle left over from the Big Bang. Maybe it's a relic of time's birth, a cosmic fossil from the instant reality first learned to tick. This idea is so radical it's already reshaping missions years before launch. Teams at NASA and the European Space Agency are retooling future dark matter detectors to listen for similar time signatures, hunting for the faint vibrational echoes that could confirm the connection. Imagine strapping a stethoscope to the universe's chest, not to hear its heartbeat, but the moment its heartbeat began. Yet the most tantalizing possibility isn't just about solving dark matter's identity. It's about rewriting cosmic history. If dark matter helped forge time's arrow, then the reason we can't detect it through normal means might be because it doesn't just exist in our universe. It could be a shadow cast by time's quantum scaffolding, a ghostly imprint from the moment causality itself flickered to life. The satellite's final act was to hand us a new lens, one that doesn't just peer into space, but into the very architecture of reality. And if dark matter is the mortar holding time's bricks together, then we're not just mapping the universe's hidden mass anymore, we're reading its blueprints. The satellite's erratic pulses didn't just rewrite our understanding of time, they cracked open a door to realities beyond our own. Those strange, rhythmic signals, once dismissed as instrument failure, now pulse at the heart of one of physics' most electrifying debates. Could we be hearing echoes from parallel universes? The idea isn't as far-fetched as it sounds. If time itself stuttered into existence in our universe, flickering like a faulty light bulb before stabilizing, why couldn't other cosmic bubbles have experienced entirely different births? Some theorists argue those anomalous patterns in the data aren't just noise, they're interference, like overlapping radio stations bleeding into each other across dimensional static. Picture this, the multiverse as a vast ocean, each universe a bubble rising from the depths. Most bubbles never touch, drifting apart in the cosmic foam. But sometimes, especially in those first chaotic moments, they might brush against one another, leaving faint imprints. The satellite's damaged sensors, tuned to frequencies no pristine instrument could catch, might have picked up the equivalent of a neighbor's shadow, a whisper from a reality where time flows backward, or in loops, or not at all. It's like pressing your ear to a shared wall in an apartment building and catching fragments of a conversation in a language you've never heard. The math behind this is both elegant and mind-bending. Quantum gravity models have long suggested that the earliest universe resembled a frothing sea of potentialities, where space-time wasn't yet firmly stitched together. In that primordial chaos, alternate timelines might have branched off like capillaries in a lung, only for most to collapse back into quantum foam. But a few could have stabilized, growing into full-fledged universes with their own unique laws. The satellite's pulses align eerily well with simulations of these branching events, as if we're detecting the aftershocks of cosmic mitosis, the moment our universe split from others we'll never see. This isn't just theoretical poetry. The idea gains traction from an unexpected corner, black holes. When matter falls into a singularity, general relativity says it's crushed out of existence. But quantum mechanics insists information can't be destroyed. The multiverse theory offers a compromise. What if that information isn't lost, but shunted into a parallel reality? The satellite's data hints that similar bleed-through might have happened in reverse during the Big Bang, with quantum fluctuations from adjacent universes imprinting onto our own. It's as if the cosmos has a backstage, and for one fleeting moment, a broken satellite pulled back the curtain. Of course, skepticism runs deep. Critics point out that multiverse theories are notoriously hard to test until now. The satellite's pulses provide something rare in theoretical physics, a potential fingerprint. If those signals can be mapped to specific quantum gravity models, we might have our first empirical window into the multiverse. Future detectors designed to mimic the satellite's strategic imperfections could hunt for recurring patterns in cosmic static, like listening for a familiar melody in a symphony of white noise. The most tantalizing possibility, if alternate universes exist and if their gravitational imprints linger in our spacetime, then time's arrow might not be universal. Some universes could experience time in reverse, others in fractured fragments. Our linear march from past to future might be just one flavor of time in a vast cosmic buffet. The satellite's greatest legacy might not be answering questions, but revealing how many we've yet to ask. After all, if a dying machine can stumble upon echoes of creation, what other secrets is the universe keeping not just in our reality, but in the ones next door? History loves its happy accidents, the moldy Petri dish that gave us penicillin, the stray cathode rays that revealed our skeletons, but none compare to the cosmic luck of a failing satellite stumbling upon time's birth certificate. Science often paints discovery as a straight line, hypothesis, experiment, proof. Yet here's the truth: some of our greatest leaps forward come from the universe throwing us a curveball. The satellite's malfunction wasn't just a setback, it was a backdoor into realms we didn't know existed. Consider the irony: we spend billions perfecting instruments, shielding them from every conceivable error, only for breakthroughs to arrive through cracked lenses and glitching circuits. The Hubble Space Telescope's blurry vision led to sharper cosmic insights. Kepler's broken reaction wheels forced it to find planets in ways no one planned. Now this satellite joins their ranks, proving that sometimes the universe communicates not through pristine signals, but through static and stutters. What's revolutionary isn't just the discovery, it's the paradigm shift. For centuries, we've treated noise as the enemy, something to filter out in pursuit of clarity. But what if the noise is the signal? Think of it like listening to a vinyl record. The pops and cracks might seem like flaws, but to a trained ear, they reveal the record's history, every scratch a story. Similarly, the satellite's malfunctions acted like a cosmic needle, tracing grooves in reality we didn't know were there. This begs a thrilling question: how many other cosmic truths are hiding in the artifacts we've been discarding? Astronomers routinely toss corrupted data from faulty sensors. Particle physicists dismiss anomalous readings as equipment errors. But what if we've been throwing away pieces of the puzzle? The satellite story suggests we might need a new approach, not just building better detectors, but designing ones that fail strategically, tuned to catch the whispers only imperfection can hear. The implications ripple beyond astronomy. Medicine thrives on accidental discoveries, from pacemakers born from misplaced electrical impulses to cancer drugs stumbled upon in soil samples. Even technology follows this pattern. The post-it note emerged from a failed adhesive, the microwave oven from a melted candy bar in a radar lab. Serendipity isn't just luck, it's the universe's way of short-circuiting our assumptions. So here's the challenge science faces now. Do we keep chasing perfection, or do we leave room for glorious accidents? The satellite's final gift was a lesson in humility. The cosmos doesn't always reveal itself through the channels we design. Sometimes it waits for a crack in the system, a fleeting gap where reality sneaks through. And if a half-dead machine can rewrite the story of time, imagine what other secrets might be hiding in the static, just waiting for the right broken tool to listen. Science thrives on pushing boundaries, but where do we draw the line between discovery and recklessness? The satellite's accidental breakthrough has sparked a fiery debate. Should we deliberately damage future space telescopes to recreate its miraculous flaw? On one side, pioneering researchers argue that controlled, imperfection experiments could unlock doors we didn't know existed. Imagine intentionally misaligning a sensor's shielding or tweaking its firmware to amplify cosmic noise, potentially revealing hidden layers of reality like peeling back the universe's wallpaper. One team at the European Space Agency has already proposed modifying an aging orbital telescope, calling it cosmic pareidolia engineering, designing instruments to find patterns in their own failures. Yet critics counter with a chilling reminder: we still don't understand why this particular malfunction worked. Space isn't a laboratory where variables can be isolated. That damaged satellite didn't just passively observe, it interacted with spacetime in ways we can't yet model. Theoretical physicist Dr. Lin Y warns of quantum backscatter, where probing primordial signals might inadvertently alter them, like shouting into a canyon and changing the echo's shape. There's even speculation that intense observation of these time ripples could create feedback loops, potentially destabilizing delicate quantum structures that underpin reality itself. It's the observer effect on a cosmic scale peering at the universe's foundations might make them shift beneath us. The parallels to past scientific dilemmas are striking. When physicists first split the atom, few anticipated the chain reactions it would unleash. Nuclear power brought both clean energy and existential threats. Similarly, prying open time's quantum seams could reveal unimaginable energy sources or unpredictable vulnerabilities. Astronomer Dr. Rafael Costa frames it starkly. We're debating whether to jury-rig our satellites into metaphysical crowbars, prying at reality's door without knowing what's on the other side. Ethicists propose a middle path, retrofitting decommissioned satellites first, creating sacrificial instruments far from Earth's orbit. The privately funded Kronos initiative plans to redirect 3 aging weather satellites into deep space, gradually introducing engineered flaws while monitoring for both scientific data and spacetime anomalies. It's a cautious approach, but as MIT's Dr. Priya Chatterjee notes, caution has never discovered anything. The first sailors didn't stay in sight of shore because the risks were known, they went because the rewards were unimaginable. What makes this debate so profound is that it's not just about methodology, it's about philosophy. Are we hunters chasing truth at any cost, or gardeners carefully tending reality's fabric? The broken satellite's legacy may ultimately be this question, written across the stars in static and stardust. How much should we risk to understand the universe when the universe itself might be listening back? The moment those primordial time ripples hit scientific journals, the world didn't just take notice, it collectively lost its mind. Within hours, the discovery metastasized from academic circles into viral obsession. Twitter birthed 1,000 memes, glitching clocks captioned "me trying to adult," distorted footage of celebrities with the tag #TimeStutter challenge, even a surreal trend of people filming themselves walking backward while pretending to unexperience their morning coffee. TikTok's algorithm, that relentless dopamine engine, latched onto the cosmic weirdness with videos set to eerie synthwave tracks, their creators musing about whether déjà vu was just our brains brushing against alternate timelines. But the real surprise wasn't the internet's chaos, it was how deeply the discovery resonated beyond irony-drenched screens. Religious scholars pored over ancient texts, pointing to passages in Hindu cosmology describing cyclical universes, or Kabbalistic teachings about broken vessels in creation. Buddhist monks drew parallels to the concept of kalpas, eons, where time itself dissolves and reforms. Even the Vatican's astronomers issued a measured statement suggesting the findings might align with Augustine's idea of time as a property of the created world rather than the divine. Meanwhile, conspiracy theorists, never ones to be outdone, spun elaborate yarns about government time travel experiments, conveniently ignoring that the satellite was Canadian. What made this cultural moment so extraordinary was its universality. Most quantum physics breakthroughs spark polite headlines before retreating behind paywalls. But this tapped into something primal, the human need to wrestle with time's nature. Late-night hosts ditched politics to riff on cosmic jokes. A Berlin art collective projected the satellite's pulse data onto the Brandenburg Gate, turning quantum fluctuations into a rave light show. Even financial markets twitched, with tech stocks briefly surging on rumors of temporal computing startups. The satellite story became a Rorschach test for the collective imagination. Sci-fi authors rewrote drafts to incorporate the new physics. Video game studios scrambled to patch realistic time mechanics into upcoming titles. A particularly inspired fan even recreated the satellite's final moments in Minecraft, complete with blocky glitches that mimicked spacetime's birth pangs. But beneath the memes and merchandising, yes, someone actually sold time's first breath. Scented candles lay a profound shift. For the first time in decades, cutting-edge cosmology wasn't confined to lecture halls. It became dinner table conversation, a shared cultural touchstone proving that when the universe whispers its secrets, everyone leans in to listen. Perhaps the most telling response came from an unexpected corner: poetry. Within weeks, literary journals overflowed with verses wrestling with the satellite's legacy. One especially haunting piece, published in the Paris Review, imagined the dying machine as a metal Icarus melting not toward the sun, but into time's cradle. That's the magic of this discovery. It didn't just give scientists new equations to solve. It gave humanity new metaphors to live by. In an age of division, here was a rare truth that bound us together: the awe of realizing our clocks don't just measure time. They carry its scars. Art has always been science's most eloquent interpreter, translating cold data into something that resonates in the gut. When news of the satellite's discovery spread, creatives didn't just report it, they remixed it. Take composer Ilara Voss, who spent 3 weeks converting those erratic pulses into musical notation. The resulting symphony, 13.8, opens with a single violin mimicking the satellite's first glitch, a wavering note that shatters into dissonance before coalescing into eerie harmony. Audiences at the premiere described weeping uncontrollably during the second movement, when the cellos recreate time's first stuttering clicks. There's something about hearing creation's birth pangs, Voss told The New Yorker, that makes your bones remember how young we really are. Meanwhile, best-selling sci-fi author Kiran Mendez took the scientific papers and spun them into The Broken Clock, a novel where archaeologists from a far future civilization uncover the satellite's wreckage. In his tale, the pulses aren't just echoes, they're a message from the universe's architects, intentionally left in the static for civilizations mature enough to decode them. The book's most chilling passage describes a character listening to the raw data stream. It wasn't sound, it was the universe clearing its throat before speaking. Filmmakers followed suit. A Sundance-winning director shot an experimental short using only the pulse patterns to control strobe lights, casting shadows that flickered like time itself unspooling. Viewers emerged nauseated but euphoric, as if they'd glimpsed something forbidden. Even the art world got involved. A controversial Berlin installation projected the signals onto human volunteers, their skin becoming living oscilloscopes that twitched with primeval rhythms. This creative frenzy reveals a profound truth about how humanity processes discovery. Science gives us the facts, but art gives them meaning. When researchers published the satellite's data, they included equations and error margins. When artists interpreted it, they gave us goosebumps. There's a reason NASA commissioned painter Robert McCall to visualize space missions. Some truths bypass the intellect and speak directly to the soul. The most poignant response came from an unexpected source: children. Elementary school teachers reported students drawing crayon galaxies with jagged edges, explaining that time used to be spiky. A viral TikTok showed toddlers building block towers only to knock them down in stuttering intervals, chanting "Big Bang" with each collapse. These unprompted reactions suggest something fascinating: that the satellite story taps into instincts older than civilization itself. What makes this cultural moment unique isn't just the art it inspired, but the dialogue it sparked between disciplines. Physicists now consult with composers about waveform aesthetics. Sci-fi authors fact-check their plots with quantum theorists. At MIT's Media Lab, engineers and painters collaborate on temporal canvases that visualize space-time's grain. The satellite didn't just change how we see the universe, it changed how we sing, write, and dream about it. Perhaps this is how paradigm shifts truly settle in, not through equations alone, but through the stories we wrap around them. When Copernicus displaced Earth from the universe's center, it took Shakespeare's plays and Donne's poetry to help culture digest the blow. Now, as we grapple with time's fractured origins, artists are once again serving as interpreters for a reality stranger than fiction. The satellite's pulses may have been faint, but their echo in human creativity deafening. Funding the next leap, governments and private entities are now racing to fund follow-up missions. The European Space Agency has greenlit a project to launch a time telescope designed to study these primordial signals intentionally. Meanwhile, tech billionaires are investing in quantum sensors that could detect even fainter echoes. The satellite's legacy is a new gold rush in cosmic exploration. The European Space Agency's Time Telescope isn't just another satellite, it's a radical reinvention of how we observe the cosmos. Unlike traditional telescopes that capture light, this instrument is designed to detect space-time's subtle vibrations, much like a seismograph listens for earthquakes. Engineers are outfitting it with quantum accelerometers so sensitive they could theoretically measure the gravitational ripple of a hummingbird's wings from orbit. The mission's lead scientist, Dr. Elena Vasquez, compares it to building a microphone for the Big Bang's echo. But here's the catch: to catch these whispers, the telescope must intentionally incorporate strategic flaws, calibrated glitches that mimic the original satellite's serendipitous breakdown. It's a paradox at the heart of this new era. To peer deeper into reality's fabric, we might need to engineer imperfection. Private ventures are taking even bolder swings. A Silicon Valley consortium backed by 4 major tech billionaires recently unveiled Project Looking Glass, an array of quantum sensors they claim can detect time ripples 100 times fainter than the original satellite's discovery. These aren't your typical lab instruments. They're housed in abandoned missile silos, shielded from cosmic interference by half a mile of bedrock. The project's chief architect, a former AI startup founder, insists they're not just chasing science. If we can harness these signals, we're talking about fundamentally new computing architectures. Imagine processors that calculate using space-time itself, Skeptics argue it's speculative at best, but the venture's funding suggests true believers are all in. Meanwhile, NASA are quietly repurposing its aging Chandra X-ray observatory for an unprecedented second act. By tweaking its sensors to hunt for time shadows, subtle distortions in X-ray emissions that could hint at primordial spacetime fluctuations, they're proving that breakthrough science doesn't always require billion-dollar hardware. Sometimes it's about seeing old tools in radical new ways. Chandra's deputy project manager puts it bluntly, "We've spent decades polishing lenses to eliminate aberrations. Now we're asking, what if those aberrations are the treasure map?" The global rush isn't just about scientific prestige. It's a recognition that whoever cracks this cosmic code could unlock technologies beyond our wildest imagination. Quantum communication networks immune to hacking. Energy systems tapping into spacetime's inherent fluctuations. Even theoretical constructs like causality engines devices that could, in principle, calculate the probability of future events by reading time's earliest imprints. No wonder national security agencies are suddenly funneling black budget money into these missions. Yet for all the high-tech arms race, some of the most promising work is happening in university basements. A Cambridge PhD student recently jury-rigged a radio telescope with parts from a scrapped MRI machine, discovering that its electromagnetic interference patterns accidentally amplified certain quantum signatures. Her makeshift detector cost less than a used car but captured anomalies that billion-dollar arrays missed. It's a reminder that in this new frontier, ingenuity often trumps budgets. The next great leap might not come from a gleaming lab but from a tinkerer's garage. What's unfolding isn't just a series of missions, it's a philosophical shift in how we explore. For centuries, science sought to eliminate noise and error. Now, we're learning that reality's deepest truths might hide in the static. The original satellite didn't just give us new data, it handed us a new lens. And through that lens, the universe looks stranger, richer, and far more mysterious than we ever dared to dream. Skepticism isn't just a roadblock in science, it's the guardrail that keeps discovery honest. While the satellite's pulses have electrified much of the physics community, a stubborn contingent remains unconvinced. Their argument hinges on Occam's razor. Shouldn't we exhaust every mundane explanation before rewriting cosmology? Dr. Henrik Voss, a renowned astrophysicist at the Max Planck Institute, leads the charge, calling the signals a Rorschach test for theorists. His team's simulations suggest the pulses could stem from something far less exotic: vibrations in the satellite's own damaged power supply, magnified by cosmic radiation into false patterns. Extraordinary claims require extraordinary evidence, he insists, and right now we're staring at static that might be a symphony. The push for verification is already reshaping observatory schedules worldwide. At the Atacama Large Millimeter Array in Chile, astronomers have repurposed 34 radio dishes to scan the same patch of sky where the satellite detected its anomalies. Meanwhile, the newly upgraded Green Bank telescope in West Virginia is listening for similar pulses at frequencies the original satellite couldn't access. The goal isn't just replication, it's triangulation. If these signals are real, they should imprint on multiple instruments in predictable ways, like a shadow cast from different angles. But here's where the skeptics face their toughest hurdle. The pulses aren't just repeating, they're evolving. Independent analyses from Tokyo to Cape Town show the signals drifting in frequency over time, matching theoretical models of quantum decoherence in the early universe. It's as if we're watching time's first vibrations fade like ripples in a pond, a fingerprint that instrumental noise simply can't forge. Even critics admit the data has an eerie coherence. It's either the breakthrough of the century, quips MIT's Dr. Leela Chen, or the most elaborate equipment failure in history, the debate reveals a deeper tension in how science grapples with paradigm shifts. When the first evidence for black holes emerged in the 1960s, eminent physicists dismissed it as mathematical fantasy. Dark matter faced decades of ridicule before becoming textbook fact. Now history might be repeating itself, not because the skeptics are wrong, but because science moves in stages from denial to disbelief to reluctant awe. What's unfolding is less a conflict than a necessary dance. Every revolutionary discovery needs its doubters, the voices demanding tighter controls, cleaner data, sharper logic. They're the reason the scientific method works. But when radio telescopes in 5 continents start humming the same cosmic tune, even the staunchest critics might soon find themselves swayed by the music of a universe far stranger than we ever imagined. The Nobel Prize has always been a spotlight that illuminates individual genius, but what happens when a discovery defies the very idea of solitary brilliance? The satellite's revelation has sparked a fierce debate in academic circles, whose names deserve to be etched in history for this paradigm-shifting moment. On one side, engineers argue their case. They built the machine that failed so perfectly, turning a dying satellite into an accidental time machine. Every glitch, every fractured circuit was the result of precise craftsmanship pushed beyond its limits. Without their expertise in materials science and orbital mechanics, there would have been no malfunction to begin with, no cosmic static to decode. Then there are the data analysts, the unsung heroes who sifted through mountains of noise to find a whisper. They didn't just notice the anomaly, they recognized it as something impossible, something worth chasing. One team member described the process as listening for a single wrong note in a symphony performed by an orchestra of black holes. Their algorithms, originally designed to filter out interference, became the key to unlocking a signal no one knew existed. But let's not forget the theorists, those who scribbled equations on chalkboards decades ago, dreaming of quantum gravity's fingerprints. Their papers, once dismissed as speculative fiction, turned out to be the roadmap for this discovery. The pulses matched their predictions with eerie precision, as if the universe had been waiting for someone to finally read its hidden script. The Nobel Committee now faces an existential dilemma. Their tradition of honoring up to 3 individuals collides with the reality of modern science, where breakthroughs are increasingly collective, messy, and serendipitous. Some propose awarding the prize to the entire collaboration, a radical departure from precedent. Others suggest recognizing the satellite itself, a nod to the role of chance in discovery. This isn't just about trophies or titles. It's a referendum on how we value scientific progress. Do we immortalize the lone genius or celebrate the tangled web of effort that makes revelation possible? The satellite story reminds us that science isn't a relay race with a single finish line. It's a mosaic where every cracked tile contributes to the picture. And sometimes the most profound truths emerge not from perfection, but from the beautiful, broken edges. Universities haven't seen this kind of intellectual whiplash in decades. Overnight, cosmology syllabi went from tidy timelines of the Big Bang to sprawling flowcharts riddled with question marks. At Cambridge, professors are hastily scribbling addenda to lecture notes, their once neat diagrams of cosmic inflation now scribbled over with jagged arrows labeled quantum stutter. And dark matter scaffolding. Graduate admissions committees report a flood of applications from physics students who, just a year ago, might have chased particle accelerators or quantum computing. Now they're all asking the same thing: how do you specialize in studying time's birth defects? The real revolution isn't just in what's being taught, it's in how. Science education has long been a parade of polished conclusions, with textbooks presenting discoveries as inevitable stepping stones. But the satellite story is rewriting pedagogy itself. MIT's introductory astrophysics course now starts with a week-long dissection of the mission's raw telemetry data, forcing students to grapple with the same noisy signals that baffled seasoned researchers. "We're teaching them to love the mess," says Dr. Naomi Park, who redesigned Yale's curriculum. If a glitch can upend cosmology, what other truths are hiding in the data we've been trained to discard? High school classrooms are catching the wave too. A viral lesson plan from a Texas physics teacher has students deliberately sabotaging their experiments, misaligning laser pointers, unbalancing pendulums, then hunting for unexpected patterns in the chaos. One 15-year-old's botched diffraction experiment recently revealed an anomalous shadow pattern that caught the attention of a Princeton postdoc. It's hands-on proof that scientific progress doesn't always wear a lab coat. Sometimes it comes covered in duct tape and curiosity. The humanities are leaning in just as hard. Philosophy departments from Oxford to Kyoto are resurrecting ancient debates about time's nature, only now with hard data to fuel the fire. A Stanford seminar on temporality in literature juxtaposes Virginia Woolf's fluid timelines with the satellite's stuttering pulses, asking whether art anticipated science's latest revelation. Even theology classes are buzzing when a Notre Dame professor suggested the findings might align with Augustine's concept of time as a created property. Her lecture hall overflowed with STEM majors auditing the discussion. But perhaps the most profound shift is in how failure is framed. For generations, science fairs rewarded flawless methodology and clean results. Now, a growing movement celebrates glitch exhibitions, where students showcase experiments gone awry, the fuzzy images, the garbled data, and theorize about what the noise might hide. It's not just academic rebellion, it's training a new generation to listen for the universe's off-key notes. After all, the satellite didn't just teach us about time. It taught us how to learn. For centuries, philosophers have treated time as either an eternal river or an illusion, but the satellite's dying transmission shreds both assumptions. If time stuttered into existence like a faulty engine turning over, then the ancient question takes on new urgency. Could it one day sputter out? The data doesn't show an expiration date, but it reveals something just as startling: time isn't some invincible backdrop to reality. It's fragile, it had a childhood, and if it grew, might it also decay? This isn't just theoretical musing. The satellite's pulses align eerily with certain quantum gravity models suggesting time could become unstable under extreme conditions, near black holes, in the far future's heat death, or during vacuum decay events. Picture a cosmic clock winding down, its gears grinding slower until one day, silence. The terrifying beauty of this idea isn't that time might end, but that its mortality would be written into its birth certificate. Those early stutters weren't glitches, they were time learning to walk, and like all living things, what learns must one day forget. Theologists and philosophers are scrambling to reconcile this with age-old concepts of eternity. St. Augustine once argued that time was created with the universe. Now we may have evidence he was literally correct. Buddhist scholars point to parallels with the Kalpa cycle, where universes breathe in and out of existence. Even secular ethicists are grappling with the implications. If time is finite, not just in practice but in principle, does that change how we value the present? Free will debates have reignited with fresh intensity. If time's arrow stems from quantum asymmetry in those first moments, as the satellite's data suggests, then every choice we make rides atop a cascade of cause and effect that began before atoms existed. Are we truly authors of our fate, or are we reading lines from a script written in the universe's infancy? Some determinists claim victory, but others see nuance. The same quantum randomness that seeded time's arrow might also inject genuine unpredictability into human decisions. Perhaps the most profound shift is in how we perceive reality's scaffolding. We used to think of space-time as a stage static, unchanging. Now we know it's more like a living thing, born from chaos, shaped by dark matter, still bearing scars from its earliest tremors. That changes everything. If the stage itself has a history, a personality, maybe even a lifespan, then all the dramas played out upon it, galaxies colliding, civilizations rising, are part of something far grander and more mysterious than we ever imagined. The satellite didn't just give us new data, it handed us a new mythology. The hunt for time zero isn't just a scientific challenge, it's a race against the universe's best hiding spot. Imagine trying to pinpoint the exact moment a light bulb flickers on in a thunderstorm, but the storm is the Big Bang, and the light bulb is the birth of time itself. That's the scale of precision required to isolate those first fragile ticks of existence from the cosmic noise. Teams at CERN and the Perimeter Institute are now feeding the satellite's pulses into quantum supercomputers, algorithms sifting through the data like archaeologists brushing dust off a 13.8 billion-year-old stopwatch. The goal: to find the pulse that doesn't just stutter but begins. What makes this search so revolutionary isn't just the technical audacity, it's the philosophical Pandora's box it cracks open. For decades, asking what came before the Big Bang was like asking what's north of the North Pole, nonsensical by definition. Time, we thought, began with the universe. But if these pulses reveal a before, even a quantum flicker of it, everything changes. Some theorists speculate time zero might not be a hard boundary, but a phase transition, like steam condensing into water. In this view, the Big Bang wasn't the absolute beginning, just the moment the universe cooled enough for time as we know it to crystallize. The computing power required borders on the absurd. To reconstruct time's first attoscons, researchers are borrowing techniques from cryptography and even Wall Street high-frequency trading, training neural networks to recognize patterns no human could spot. One Berkeley team repurposed a Bitcoin mining rig, its processors now crunching cosmic data instead of currency hashes. The irony is delicious. A machine designed to chase artificial scarcity now hunts for the ultimate abundance, the universe's first moments. Yet the real magic happens at the intersection of disciplines. Materials scientists are studying superconductors near absolute zero, hunting for analogs to spacetime's early instability. Musicians collaborate with physicists, translating pulse data into sonic landscapes, because sometimes the ear detects rhythms the eye misses. Even philosophers are back in the lab, debating whether time zero's indeterminacy supports radical free will or proves we're all just riding quantum ripples from creation's first shiver. The most tantalizing possibility: time zero might not be a single moment but a spectrum. Just as light exists beyond visible wavelengths, the dawn of time could have phases we've never perceived. Some models suggest the earliest, proto-time, behaved more like a quantum probability field, with causality flickering in and out like a shaky radio signal. If so, our linear experience of past, present, and future might be like seeing only one color of a rainbow, a limited slice of time's full nature. This search rewrites what we consider possible. For centuries, science avoided questions about ultimate origins, dismissing them as metaphysics. Now, we're building tools to probe them empirically. Whether we find time zero or hit another horizon, the attempt alone is transformative proof that some mysteries aren't meant to daunt us, but to pull us forward into deeper wonder. After all, if a broken satellite could hear time's first whispers, Who knows what other dawns we might yet overhear? Time crystals sound like something ripped from a sci-fi novel, materials that break time's symmetry, ticking forever without energy, like a clock that winds itself. In labs from Harvard to Google Quantum AI, physicists have coaxed these strange structures into existence using lasers and supercooled atoms, watching as they pulse in perfect, self-sustaining rhythms. But here's where it gets cosmic. The patterns they produce bear an uncanny resemblance to those erratic pulses from the dying satellite. It's as if researchers accidentally recreated the universe's first heartbeat in a test tube. The connection isn't just poetic. Time crystals thrive on imperfection, their stable oscillations emerging from controlled disorder, much like the satellite's broken sensors revealing order in cosmic chaos. This parallel has theorists buzzing. Could the early universe have behaved like a gargantuan time crystal, its space-time lattice pulsing in a quantum dance before settling into the steady flow we know today? The math hints at yes. Simulations show that under the extreme conditions of the Big Bang, matter might have naturally arranged into phases that echo time crystal behavior, with quantum fluctuations acting like nature's laser pulses, setting reality's rhythm in motion. Practical implications are already materializing. Time crystals' resilience to noise makes them ideal for quantum computers, where they could stabilize qubits against decoherence, the same way the satellite's flaws amplified rather than obscured its discovery. And then there's timekeeping. Atomic clocks, already precise to 1 second in billions of years, could leap forward by incorporating time crystal principles, their ticks synced to the same quantum beats that might have governed the infant universe. But the most tantalizing idea, that we're not just mimicking the early cosmos in labs, we're holding up a mirror to it. If time crystals truly share DNA with spacetime's primordial structure, then studying them could be our closest shortcut to probing time zero itself. Every pulse in a lab-grown crystal might whisper secrets about how time first learned to flow, offering clues to questions the satellite's data can't answer alone. The universe's oldest tricks, it seems, are still playing out in today's experiments, just on a scale we're finally learning to see. Science has always thrived on competition. The race to publish first, the scramble for funding, the national pride of planting flags on cosmic frontiers. But something remarkable happened when that dying satellite beamed its final data back to Earth. Laboratories normally locked in intellectual arms races started emailing each other codes to decrypt the signals. Researchers from countries with frosty diplomatic relations found themselves on late-night Zoom calls, debating quantum fluctuations over pixelated screens. The discovery didn't just rewrite physics, it temporarily rewired human nature, proving that when faced with a mystery this profound, even rivals can become collaborators. Take the joint statement issued by the U.S. National Science Foundation and the Russian Academy of Sciences, two institutions that hadn't shared a byline in years. Within weeks of the satellite's discovery, they'd pooled telescope time from New Mexico to Siberia, creating a continuous monitoring network no single nation could achieve alone. Or consider the Geneva workshop where Iranian and Israeli physicists traded equations on a chalkboard, their governments' tensions momentarily eclipsed by the sheer gravitational pull of the puzzle before them. One attendee later joked that the only heated arguments were about Planck scale mathematics, not politics. This isn't just about sharing data, it's about dismantling barriers. The European Space Agency's new Quantum Gravity Task Force includes scientists from India, South Africa, and Brazil, countries traditionally excluded from cosmology's inner circle. Their insights, drawn from diverse academic traditions, have already uncovered patterns in the satellite's pulses that Western models missed. A Nairobi-based team, for instance, noticed rhythmic variations resembling East African drumming cycles, an observation that led to the breakthrough idea of treating time's birth pangs as vibrational modes rather than linear events. Even private space companies, notorious for hoarding intellectual property, are playing nice. SpaceX rerouted a Starlink satellite to relay data from a Chinese lunar probe studying analogous quantum echoes in the moon's tidal-locked crust. Meanwhile, Elon Musk and Jeff Bezos, better known for their billionaire feud, quietly co-funded a repository where any researcher, regardless of affiliation, can access raw signal files. It's as if the universe handed humanity a cipher so tantalizing, it temporarily overrode our instinct to compartmentalize knowledge, the most telling symbol of this détente. The makeshift war room at CERN, where physicists from 32 nations crowd around screens displaying real-time pulse analyzers, coffee cups bear labels in a dozen languages, whiteboards mix Cyrillic and Mandarin with Latin equations, and the only uniform is the occasional gasp when someone spots a new anomaly. One grad student described it as a UN summit where everyone actually listens. Yet the true test lies ahead, as funding bodies weigh whether to prioritize national prestige over collective progress, and as publishers debate open access rules for this unprecedented dataset. The satellite's ultimate legacy may not be the science it enabled but the precedent it set. For a few fleeting months, humanity functioned as a single intellectual organism, its curiosity outweighing its divisions. Whether that unity survives the transition from discovery to interpretation remains an open question. But for now, in labs across the globe, the pulse of collaboration beats in time with the echoes of creation itself. Every paradigm-shifting discovery carries its own shadow. The whispers at the edges of consensus, the alternate explanations that bloom where uncertainty lingers. The satellite's pulses were no exception. Within days of the data going public, conspiracy forums lit up with wild theories. Alien megastructures broadcasting their existence, secret government time experiments leaked by accident, even glitches in a simulated universe revealing the code beneath our reality. One particularly viral post claimed the pulses matched Fibonacci sequences found in ancient pyramid designs, proof of lost civilizations with cosmic knowledge. Never mind that the Fibonacci sequence appears everywhere from sunflower seeds to galaxy arms. When the universe hands humanity a mystery, some will always reach for the most dramatic interpretation. What makes these theories so persistent isn't their plausibility, it's their emotional resonance. Faced with something as incomprehensible as time's birth pangs, the human brain rebels against cold statistics and error margins. We crave stories, patterns, intentionality. A malfunctioning satellite stumbling upon creation's echo feels anticlimactic compared to the idea of ancient astronauts or rogue AI nudging us toward enlightenment. This tension reveals science communication's tightrope walk, how to honor the public's hunger for wonder while grounding speculation in evidence. The simulated universe theory gained particular traction, thanks to its veneer of techno-philosophical sophistication. Silicon Valley influencers latched onto the idea that the pulses resembled processor lag in a cosmic mainframe, their tweets ricocheting through algorithms faster than peer-reviewed papers could debunk them. Never mind that the very concept of a simulation requires a baseline reality where time already exists to run the program. A logical loop even the slickest TD talk can't untangle. But when astrophysicists pointed this out, the response was telling. You're just saying what the simulation wants you to say. Here's where the real lesson lies. These theories flourish not because people reject science, but because mainstream explanations often fail to convey the sheer awe these discoveries deserve. When researchers describe quantum gravity in dry equations, they cede the emotional high ground to storytellers who package half-truths as epiphanies. The antidote isn't condescension, it's better storytelling. Imagine if every press release about the satellite's data came with a sonification of those primordial pulses, letting people hear time's stuttering birth. Or interactive visualizations showing how quantum fluctuations sculpted the cosmos, making abstract concepts visceral. The conspiracy theories also reveal an uncomfortable truth about scientific authority. In an age where anyone with Wi-Fi can access RZIV preprints but few have the training to interpret them, credentialed experts compete with charismatic amateurs armed with slick YouTube edits. When a tenured cosmologist and a self-proclaimed time researcher with a Patreon clash online, the algorithms often favor drama over nuance. Some institutions are adapting. The Perimeter Institute now trains physicists in viral science communication, while the American Astronomical Society hosts Reddit AMAs vs. Misinformation workshops, yet there's unexpected value in these fringe ideas. Like cosmic rays colliding with atmosphere, they spark cascades of public engagement that sometimes lead to legitimate insights. The simulated universe craze, for all its flaws, inspired fresh approaches to testing quantum gravity via computational limits. Even the wildest alien signal theories prompted SETI to reevaluate its detection protocols. The key is distinguishing productive speculation from disinformation, not by silencing outliers, but by flooding the zone with clearer, more captivating truths. At its core, this isn't just about one satellite's data. It's about how humanity processes the incomprehensible. Before Newton, comets were omens. Before Pasteur, illness was divine punishment. Every leap in understanding begins with misinterpretations that, in their own flawed way, try to make the universe feel knowable. The pulses from that broken machine didn't just challenge physicists, they held up a mirror to our timeless need for narrative, reminding us that the most powerful discoveries aren't just measured in sigma values, but in their ability to make the cosmos feel alive with meaning. The next decade in physics won't just build on the satellite's discovery, it will be rewritten by it. Laboratories that once chased ever finer measurements of the cosmic microwave background are now retooling to hunt for spacetime's quantum whispers, their blueprints littered with intentional flaws modeled after that fateful malfunction. At CERN, engineers are repurposing particle colliders to simulate the extreme conditions of the universe's first attoscons, while underground labs from South Dakota to Japan are upgrading neutrino detectors to catch the faintest tremors in time's fabric. It's as if the entire field has taken a collective breath and realized we've been listening to the cosmos with noise-canceling headphones, filtering out the very static that holds the answers. But hardware is only half the revolution. Theoretical physics, long divided between competing quantum gravity models, now has something rare: actual data to test against. String theorists are scrambling to adjust their vibrational membranes to match the satellite's pulses, while loop quantum gravity teams celebrate how closely the signals align with their predictions of spacetime's granular structure. Even dark matter research has pivoted, with new models suggesting the mysterious substance might be less like a cloud of invisible particles and more like time's fossilized scaffolding, its gravitational pull a relic of how reality first knit itself together. The irony is delicious. A broken satellite didn't just hand physicists a new puzzle, it gave them a Rosetta Stone to finally translate their most abstract equations into observable truth. Yet the boldest experiments aren't happening in labs, they're unfolding in supercomputer simulations. Teams at Princeton and Berkeley are reconstructing the universe's birth not as a smooth expansion, but as a quantum froth where causality flickered like a faulty light bulb. Early results are staggering. Virtual universes seeded with similar time stutter patterns evolve galaxies that match our own with uncanny precision, right down to the distribution of cosmic voids. It's as if we've been trying to assemble a jigsaw puzzle with half the pieces missing, and the satellite's data just handed us the missing edge, the real game changer. This isn't just about refining old theories, it's about asking questions we never thought to pose. If time emerged from quantum chaos, could it do so differently elsewhere? Could pockets of the cosmos exist where time flows backward, or in loops? Future missions already on the drawing board aim to map these possibilities, from a proposed time telescope orbiting Neptune to arrays of quantum sensors buried in Antarctic ice. Even philosophy departments are joining the fray, hosting cross-disciplinary salons where physicists debate metaphysicians over whether time's arrow is a fundamental law or a cosmic accident. What makes this moment extraordinary isn't the scale of the shift, it's the speed. Normally, paradigm changes crawl through academia over generations. But when that dying satellite beamed its final transmission, it ignited a chain reaction of collaboration. Preprint servers now overflow with papers from rival research groups citing each other's work, while conferences once dominated by territorial posturing have become frenzied brainstorming sessions. The most telling sign, graduate students who began their PhDs studying black holes are now switching en masse to quantum cosmology, their dissertations rewriting textbooks before they're even printed. One thing's certain, the universe has handed us a new lens, and through it, everything looks different. Time isn't the steady river Einstein imagined. It's a current with eddies and whirlpools, its flow shaped by quantum scars we're only beginning to trace. As detectors grow more sensitive and models more daring, we're not just observers of this revelation. We're participants in it, living through the moment when humanity first glimpsed the stitches in reality's fabric. And if a single broken machine could rewrite the rules this profoundly, imagine what the next decade's tools might reveal. The clock is ticking, but for the first time, we're starting to hear how it was wound. Every heartbeat, every sunset, every fleeting thought you've ever had, they all trace back to those first stuttering moments when time itself struggled to find its rhythm. The satellite's discovery doesn't just belong to physicists in lab coats, it's woven into the fabric of your daily life, that morning coffee cooling on the counter. The way traffic lights cycle from red to green, even the aging of your favorite pair of shoes, all of it rides atop a current that began flowing before atoms existed. You're not just living in time, you're breathing its history. Consider the mundane miracles around you. A child blowing out birthday candles exists because gravity clumped stardust into stars, because quantum fluctuations in the universe's infancy became the blueprint for galaxies. The satellite's pulses remind us that the ordinary is extraordinary when you zoom out far enough. Your ability to remember yesterday and anticipate tomorrow isn't just biology, it's cosmology in action. A direct inheritance from those primordial asymmetries that tip the cosmic scales toward order. This revelation flips how we see our place in the universe. We often frame space exploration as humanity reaching outward, but the truth is more intimate. That dying satellite didn't just look back in time, it mirrored our own origins. The carbon in your bones, the iron in your blood, were forged in stellar furnaces powered by those same quantum seeds the satellite detected. You're not a passive spectator to cosmic history. You're its latest chapter, a walking testament to 13.8 billion years of refinement. There's a humbling beauty in realizing how fragile our temporal existence really is. Had those early pulses been just 1% weaker, time might never have cohered into the steady flow we rely on. No sunrises, no music, no stories passed between generations. The fact that we're here to ponder this at all is a cosmic lottery win of unimaginable odds. And yet, here we are, not just beneficiaries of time's arrow, but its custodians. Every choice we make, every artifact we create, becomes part of time's ever-lengthening chain. So the next time you check your watch or scroll through old photos, pause for a second. That ticking isn't just mechanics, it's the echo of creation's first shudder, reverberating through the ages to this very moment. The satellite's greatest gift wasn't just rewriting textbooks. It was reminding us that we're not separate from the universe's grand narrative. We're its living, breathing continuation. And if a broken machine could stumble upon such profound truths, imagine what wonders might still lie ahead, not just in the stars, but in the ordinary magic of every passing second. From a broken satellite to the birth of time itself, this wasn't just a scientific breakthrough. It was a masterclass in how the universe reveals its secrets. Think about it. We spent decades building flawless machines, polishing lenses, eliminating noise, convinced that truth lived only in precision. But reality had other plans. It took a battered, half-dead satellite, spinning through the void with its circuits failing, to show us what perfection couldn't. The cracks in its design became windows into the cosmos' deepest mysteries, proving that sometimes the most profound truths aren't found in the light, they're hiding in the static. This story isn't just about cosmology, it's a metaphor for how discovery works. History's greatest leaps often come from sideways glances, from accidents we're smart enough to notice. Penicillin growing in a petri dish left unattended. X-rays discovered because someone forgot to put away photographic plates. Even the Big Bang theory itself was initially dismissed as cosmic nonsense before the evidence became undeniable. The universe doesn't hand us revelations on a silver platter. It whispers them in the language of flaws, coincidences, and happy accidents. Our job isn't just to listen, it's to embrace the noise. And what a noise it turned out to be. Those erratic pulses from a dying machine didn't just add a footnote to physics. They tore up the textbook. Time isn't the steady, unbroken river we imagined. It's a stuttering, evolving thing, born from chaos and still carrying the scars of its infancy. Dark matter might not just be invisible mass, it could be time's ancient scaffolding. Even the laws of cause and effect, the very foundation of reality, might be cosmic accidents frozen into place. The satellite's final gift was humility, reminding us that for all our equations and theories, the universe is stranger, wilder, and more creative than we'll ever be. But here's the thrilling part. This is just the opening chapter. If a single malfunctioning satellite could rewrite our understanding of time, what else is out there waiting to be found? Maybe the next breakthrough will come from a telescope lens deliberately scratched to diffract light in new ways. Maybe a quantum computer's errors will reveal parallel dimensions. Or maybe, just maybe, the key to unlocking dark energy is sitting in a pile of discarded data, labeled as noise by some graduate student who didn't recognize the universe's handwriting. The lesson isn't to stop building perfect machines. It's to start paying attention to their beautiful imperfections, to design experiments that leave room for serendipity, to train young scientists to chase anomalies instead of dismissing them, and above all, to stay wildly curious. Because the cosmos isn't a puzzle with one solution, it's a living, breathing riddle that changes every time we think we've got it figured out. So here's to the broken things. The glitches, the cosmic typos, the moments when reality winks at us through the cracks. They're not mistakes, they're invitations. And if we're brave enough to accept them, who knows what other wonders might spill through. After all, we've just begun to read the universe's first draft. The rest of the story is ours to write.